Do men and women consume the same average number of vegetables servings per day? 25 men and 25 women were randomly selected to keep a food journal. The men ate an average of 2.9 servings of vegetables per day with a standard deviation of 0.6 servings. The women ate an average of 4.3 servings of vegetables per day with a standard deviation of 0.7 servings. Use a 5% significance level to test the claim. Let's start here with this phrase. This indicates we're dealing with a hypothesis test problem. So use a 5% significance level to test the claim that women eat more servings of vegetables per day than men on average. And then they tell us to assume equal variances. Okay, so let's start out by expressing the claim symbolically. So they're saying the claim is that women eat more servings of vegetables per day than men. So let's just, when we write the claim, we have a mean for men and we have a mean for women. And let's figure out what's the proper symbol to put between these two, right? If they say that women eat more servings of vegetables per day, that means that the women have a greater amount on average of vegetables per day than the men. So the greater than or the less than symbol here in this case based on how our means are written. If you put the mean for women on the left, then the mean for men would be on the right, and the symbol in between them would be greater than, but it would still be opening towards the women, so that's all that matters. It conveys the same information. All right, from there, let's go ahead and put our HO and HA on the paper, right? All right, so looking at the claim, we see the symbol here is a symbol that HA uses, so the claim and HA are the same in this case, right? And then we're going to look at HO. Now, HO has to express the opposite idea, so in this case it would be greater than or equal to between the two means, right? So the alternative idea, or the opposite idea, excuse me, not the alternative idea, because the alternative idea is here, but the opposite idea of this alternative hypothesis is greater than or equal to. In other words, men eat more or the same amount of vegetables as women per day. All right, now from there, let's collect the data. So when we do the data step, we should label the categories. So I'll do men and women. So M for men, W for women, obviously. Then we look here, it says 25 men, right? And 25 women. So they're both the same number, right? So N is 25 for both. Are randomly selected to keep a food journal. The men ate an average of 2.9 vegetables. So the men, the X bar is 2.9. With a standard deviation, so the men ate an average of 2.9 vegetables per day with a standard deviation of 0.6, 0.6, right, as our standard deviation. And then it says that women ate an average of 4.3 servings, so 4.3, with a standard deviation of 0.7. Then it says use a 5% significance level, so that's our alpha, right, 0.05. Okay, so we have our data. Next step is to come up with our test stat formula, so let's express it. Since the sample sizes are small, we will go ahead and use a T test stat formula. And then the top of the formula is going to have X bar for men minus X bar for women. This is to keep the order of things the same. I did men, women, so men, women, right? Be consistent in how you do this and it'll work out to be the same and all the problems will work out correctly. If you start switching the order in which you place these symbols here in the formula, you're going to mess up. Your test stat will have the wrong sign, in other words, right? So if you put men and women, then it has to be men and women here. All right, then you use your square root in the denominator. Now the fact that they said assume equal variances indicates that I'll be working with a pooled estimator for my variance. So SP squared over N1 plus SP squared over N2. Sometimes you may see this formula written with the SP squared outside and you have parentheses in 1 over N1 plus 1 over N2. I don't write it that way because when you put it into your calculator, it's actually a little faster not to have to put the parentheses. So it's just a taste issue, but it really makes no difference. It's the same exact thing algebraically. Okay, now enter your variables. X bar for men is 2.9 minus X bar for women, which is 4.3. Then the square root. Now to put this value in, we have to first calculate it, so let's do that over here. SP squared. So remember the idea is that you take the degrees of freedom for the first group, that's 25 minus 1 or 24, times this standard deviation quantity squared, plus the degrees of freedom for the second group times its standard deviation, which is 0.7 quantity squared. Okay, and then you divide by the 2 degrees of freedom, so in this case it'll be 24 plus 24, or of course 48, right? So SP squared is going to be worked out in our calculator, so we can plug it in there. So let's do that calculation quickly first. So we're going to have 24 times 0.6 squared plus 24 times 0.7 squared. And when we enter that, we get 20.4 on top. And we'll divide that by the bottom, which of course is 48, but we'll do it as 24 plus 24, just to get practice in using the parentheses there on the bottom. And we end up with 0.425. 0.425. So it's nice and easy to enter. So we can just type that in here now, 0.425 over our ends. Now our ends for both are 25, right? Plus 0.425 over 25. This one, since they had the common denominator of 25, would have been nice and easy just to do 2 times the single fraction. But, either way, we're just working it out as we traditionally work it out for most problems where you don't have those conveniences. All right, so now let's go ahead and plug in the top part in parentheses. So we'll do 2.9 minus 4.3, close that parenthesis, hit divide by the square root of. Now it's going to be 0.425 divided by 25 plus 0.425 divided by 25. All right, and when we hit enter, we get the answer negative 7.59, negative 7.59, which is a very extreme test statistic. At this point, we pretty much know that we're going to reject the null hypothesis because that test stat is too extreme to not fall into the rejection region. It's going to fall into the rejection region. But to be certain, let's calculate or create the rejection region on our drawing. That way we know precisely where it is, mainly because it's a test exercise in your class, not because realistically we have to do it. This number is always going to be in the rejection region. It's so extreme. Okay, so we draw our bell curve, label it T here because it's dealing with a T test. We look at HA and we see that the less than symbol indicates a left-tailed test. So anything that falls on this left-hand side of the curve is going to cause us to reject HO, right? So reject HO if our test stat lands there, and of course do not reject it if it lands here, right? If it lands anywhere here to the right, we will not reject HO. All right, so let's go ahead and get our critical value. Now, our critical value is going to be in the form, since it's all in one tail, it'll be T.05. So we're going to have the full alpha put into one tail. And the degrees of freedom here is going to be basically the sum of these two minus 2. So 25 plus 25 minus 2. So of course that's 48. Let's just write it that way to save space instead of doing 25 plus 25 minus 2. So in other words, the critical value that's going to go here, that critical value is a T.05, 48 value. So 48 degrees of freedom and 5% alpha all in one tail. So let's go to our 0.05 column and look up 48 degrees of freedom to figure out what our critical value is. Of course, remember, if it's on the left-hand side of the curve, it will be negative. So let's put the negative in there up front so we don't forget to do it later. All right, so let's go to our table and get our critical value. Okay, so we're looking at 0.05 and 48 degrees of freedom. So that's going to be between 45 and 50. We'll choose the value here at 45 because it's a larger critical value. That's 1.679. Okay, so we found the critical value, 1.679. So 1.679 is on the left, so it's negative 1.679. And now, of course, we know our test stat is way over here, off the charts, and definitely in the reject HO side of the curve. So our conclusion is going to be, our initial conclusion is going to be that we should reject HO and therefore support HA. All right, and now all we have to do is figure out the wording that we should use. So we're going to look over here at our claim and identify whether it's HO or HA. Because it has the less than symbol, it is HA, and because it's HA, we're going to use this phrase here. We're going to say that the sample data support the claim. And so that's our final answer. We support the claim that men consume less servings of vegetables per day than women, or that women consume more than men. So we support that claim, and that's it. So remember, the sample data says that we support the claim is our final answer.